Hello friends, so far we have seen motion in one dimension, right? That means the object or the body moves in one direction along a straight line. Okay, it may move in one direction or it may move, parallel to itself. Okay, so that is motion in one direction or motion in one dimension. But now, does it always do like that? Do the bodies always move only in one line? The answer would be no. The bodies move in a straight line, the bodies move in a plane, the bodies move in space, correct? So now, having completed what happens in a single dimension, let us switch over to motion in plane, or we call it motion in two dimensions. Okay, now why do we call it motion in two dimensions? Because for motion in one dimension, it would move maybe in this direction. Okay, and for motion in two dimensions or motion in one in plane, I would have one more coordinate here, one more coordinate axis. So if I call this x axis, this would be my y axis, correct? And in motion in two dimensions, we need two coordinates to specify the position of the object. For example, there is this point. Let us call this point P, x1 comma y1, and point Q, it is x2 comma y2. Now if this object, okay, my object initially it was at point P and now it is moving to point Q. In both the cases, I am specifying two coordinates, that is x coordinate and y coordinate of the object. Now, how does it matter? See, it is like, I have my reference point as origin here, the point of intersection of my x-axis and y-axis here. Okay, and then with reference to my origin, okay, I'm specifying the coordinates of this body as it moves from one point to the other. Okay, now it can now the quantities which we would be learning over here, they can be position of the object, or it can be displacement of the object, or it can be velocity of the object, or it can be speed of object, it can be acceleration, right? Anything, and anything over here, it will have two dimensions. Okay, and that is the reason we call this motion in two dimensions. Now again, we have earlier we have learnt about um, some vector scalars and vectors, right? Displacement as a vector quantity, and distance as a scalar, or then velocity as a vector and speed as a scalar quantity, correct? Now when a particle moves in the plane, okay, it would have certain x coordinate and certain y coordinate, isn't it? So that means if I have to express this motion in terms of vectors, correct, then I would need to specify some vector in x direction and some vector in y direction. Okay, so now here what we do is we define I cap, okay, I cap and j cap here. Now what are these I cap and j cap? They are unit vectors in x direction and unit vector in y direction. Okay, when we have motion in three dimensions, over there we will have one more axis would be z axis. So you have x axis, y axis and z axis. You have I cap, j cap and k cap, correct? So position of any object can be specified in terms of these two vectors, this I cap and j cap. Now instead of calling I bar and j bar, I am calling it I cap and j cap. When I say cap, it means unit vector. And what is a unit vector? Unit vector is a vector whose magnitude is 1 unit. Okay, now that 1 unit can be anything. If I am talking about displacement, it would be 1 meter. If I am talking about velocity, it would be 1 meter per second. It would be 1 meter per second square if I am talking about acceleration, correct? But I cap, j cap and k cap, they are unit vectors in the directions of coordinate axis selected by us, and the coordinate axis that we select, they are mutually perpendicular. Now in this case, for motion in two dimensions, we have x axis and y axis, which are perpendicular to each other. In case of motion in 3 dimensions, we would be having x-axis and y-axis and z-axis with all the 3 axes mutually perpendicular to each other. Okay, now let us see how we are going to really express these coordinates in terms of some vector quantities. For example, this point P here, okay, if I connect this point P with the origin here, I'm connecting this with origin, and then I specify the angle made by this vector OP bar. Okay, I'm calling this P bar, small p bar. Okay, if this angle is theta, correct, then how much would be x1 and how much would be y1? So what you would do here would be draw a perpendicular here and perpendicular here on the respective coordinate axis, and if you call this point A and this point B, then OA is equal to the x coordinate and OB is equal to y coordinate. Correct? So x1 and y1. Okay, x1 and y1 are the x and y coordinates of P. Now there is something more to it. I am calling this vector OP bar equal to small p bar. Okay, that means magnitude of OP bar. How much is that? It is P. Okay, so if I write magnitude of this P bar is equal to P, okay, and how much is that? Is this a right angle? Correct. So my PAO is a right angle triangle, and in this right angle triangle, my cos theta is equal to OA upon OP, and sin theta is equal to PA or AP upon OP. Correct. But what is my OA? Is it not x1 upon small p, and this is y1 upon small p here? Correct. So my x and y coordinates would be x1 is equal to p cos theta and y1 will be equal to p sin theta. Correct. Now how do we express the position in terms of your I cap and j cap? Okay, we'll express this vector. Okay, now let us try and recollect the triangle of vector addition. Okay, now what is this OP bar? Now OP bar, if I use triangle law, then that would be OA bar plus AP bar, OA bar plus AP bar, isn't it? So that is equal to P bar is equal to, now what is OA bar? OA bar is equal to magnitude of x1 into I cap, correct? So it would be x1 I cap plus, now AP bar, is it not same as OB bar, right? So it would be y1 j cap. Okay, and then your x1 is p cos theta, so it is p cos theta I cap plus p sin theta j cap. Okay, so this is your general vector equation for position of a given point over here. Now the same thing can be applied to velocities, same thing can be applied to accelerations and so on, because if you are differentiating displacement with respect to time, you are going to get velocity. If you are going to get differentiate velocity with respect to time, you are going to get acceleration. So that is how it works, and that is how we would be learning this motion in 2 dimensions. There are various interesting things that we would be coming across here, like relative velocities, or some problems like a boy walking in the rain and holding his umbrella like this. The rain is falling like that, but then he is moving in this direction. Okay, so he has to hold the umbrella like this. You must have experienced this in real life. Okay, or then a swimmer okay, there is one river and he wants to cross the river, he wants to reach the opposite bank of the river, and but then the water has got some current, it has got some direction, okay, and then in which direction he should swim, okay, he should swim straight, or he should swim like that, or he should swim like that, it depends on where he really wants to uh, reach. And we will be making use of what we have learned before. It can be triangle law of vector addition, or it can be parallelogram law of vector addition, or anything for that matter that we have done earlier, including relative velocity, which we did some time back. Okay, in the next video we are going to solve some problems for next few videos, in fact. And till then, bye bye, thank you.